We are on page 4 and we are going to be discussing and learning about the exact terms we should use when describing a wave, specifically a transverse wave. So in the diagram that we have a simple wave starting here and going up, coming back to the central position and then keeping on going, and then it repeats. So the middle position is referred to as the rest position because when it is in the middle, it is neither upwards of where it normally is, nor is it downwards from where it normally is. So it is undisturbed. So the middle is the rest position. Think of this diagram as if it were a surface water wave. Okay, and we are looking at it from the side as it passes in front of us. Okay, from left to right. Okay, and think of the middle, the rest position, as the normal level of the sea, sort of. Okay, and as you know, when there are waves, the water will go up, then come back down and keep on going. Alright, the first one, the wavelength is the distance between any two successive similar points on the wave. The symbol for wavelength is lambda, and the units are in meters. Okay, so let's start a bit from the back. The units here are meters, normal meters. The unit to measure a distance between any 2 points. We always use meters as the SI unit. Now, the symbol for wavelength, if we want to write wavelength in short, we will use this symbol. This is called a lambda. It is not a lambda, like a tin, like the word for tin in Maltese. It is not lambda, it is lambda. It is spelled like this, Lambda. As you might have figured, it is a Greek letter, okay? It is a lowercase Greek letter for L, basically. So that is lambda. The way you write it is, again, not that hard. It is similar to writing a Y upside down, okay? Where if you have the lines, okay, let's say these are the lines of your copybook or of your paper or whatever. You would write this as follows. You would start from here and go up and stop in the middle, and then come from the top and meet it there. It is that simple. It's just 2 lines. Literally a letter Y that is upside down. So the symbol for wavelength, if you wanted to write wavelength for short, like we will when we get to the equations, there will be an equation for this. This is how you write lambda. I had told you earlier on in the year that we will eventually not only be using small letters and capital letters, but we will also be using Greek letters. Okay, this is another one. So the wavelength is the distance between any two successive similar points. So here we have the example of the highest most point and the next highest most point. The distance between those two is 1 wavelength. Now, the very tops of the wave are called crests. So these that I will mark in red are called crests, meaning the highest most point of the wave. At the exact opposite, marked in pink, are the lowest most points. Those are called the troughs. Okay, one would be a trough, T-R-O-U-G-H, even though there is a G-H, it is pronounced as an F. Okay, so it's not only in Maltese that the G and the H make a funny sound. The troughs are the lowest most point in a wave. And again, the distance between one trough and another will once again be 1 wavelength. Now, even though we're saying that the wavelength is the distance between any two successive points, don't make the mistake of thinking that if we were to measure, let's say, from this rest position to this one, that would be 1 wavelength. That is not. That is only 1/2. of a wavelength. The definition is the distance between any two successive similar points, and by similar we mean if in the first one, in the one over here, it is at the rest position but it is going up, then for me to take one measurement of a wavelength, I have to find another spot that is at the rest position and it is going up. So in this case, I can either measure from here to here, or else from here to here. So from orange dot to the other orange dot, that will not be one wavelength, because the first one is from the rest position going up, going towards a crest, whereas the second one is from the rest position going to a trough. Now in this case, in this picture, we are seeing two full wavelengths, because we're starting from the rest, going to a crest, back to rest, down to a trough, and back to rest. That is one wave, and then we are repeating. So we have two full waves, which is why the distance for one wavelength is two successive similar points. That would be one full wave. The amplitude is the maximum displacement or height of the wave from the undisturbed rest position. So from the rest position, which is the middle, going to the farthest point from it, which is either a crest or a trough. Now with regards to amplitude, the larger the amplitude, the greater the amount of energy flowing along the wave. Okay, so if we take the example of the sea again, the larger the amplitude of the waves, if we take the example of the sea again, the stronger the sea is, the larger the amplitude of the waves will probably be. If there is a lot of wind, alright, or it is very bad weather, the amplitude of the waves in the sea are going to be much larger than if it is a calm day. Point number 3. The frequency of a wave is the number of waves or oscillations produced each second by the source. The symbol for frequency is F, while the units are hertz. For short, we can write hertz as capital H, Z. The word hertz comes from the surname of Heinrich Rudolf Hertz, who was a physicist that studied in depth in the nature of waves. So that is why the units for frequency are named after him. What the frequency is how many full waves are passing a particular point every second. Okay? So if in the diagram that we have at the top of page 4, these waves are taking 1 second to pass, then in that case, if in 1 second we have 2 complete waves, then that would be 2 hertz. If at a particular point a source is passing, I don't know, 1000 full waves every second, then that would be 1000 hertz. Now we can start bringing things together. The velocity of a wave is found by the following formula. Velocity is equal to the frequency multiplied by the wavelength. So velocity for short is a small v, frequency we said is a small f, and wavelength is a lambda. So v equals f lambda. Velocity is obviously measured in meters per second, frequency we said is measured in hertz, and wavelength is measured in meters. So if I want to figure out how fast a wave is, I need its frequency and its wavelength. Also, by now you should be used to this, I can be given the velocity and the frequency, and I can find the wavelength. If I wanted to write this in the triangle form, I can write it like this: v at the top, f and lambda at the bottom. If I wanted to find the velocity, therefore I would cover v and I would be left with f times lambda. If I wanted to find the frequency, I would cover f and I am left with the velocity divided by the wavelength, and so on. You should be used to using the triangle by now. Finally, the periodic time, sometimes also referred to as the period, for short written as a capital T. Okay, the periodic time or period is the time taken to make one complete oscillation or cycle, or in this case, the time it takes for one full wave to happen. The units are seconds. Obviously, if what we're talking about is time, then the units have to be seconds. Periodic time has nothing to do with the amplitude. Okay, it does not depend on the amplitude. Now, frequency and periodic time are inversely proportional in the sense that the period would be equal to 1 divided by the frequency. And also, the frequency is equal to 1 divided by the period. So if I am given one of these, I can very easily find the other by simply dividing 1 by the value that I have. So if we go back to the example at the top of page 4, we said that for all of this wave to happen, we're going to imagine that it is taking 1 second. And we said that since there are 2 complete waves, the frequency is 2 Hertz. So therefore, if I wanted to find the periodic time, which means how long it takes only one wave, I simply have to do 1 divided by 2, because we said the frequency is 2 Hertz, and that will give me 0.5 seconds. So if 2 full waves are passing every 1 second, and we have a frequency of 2 Hertz, that means that every wave is taking half a second.